Good evening, everyone. Today I will discuss about how to use Jamovi in statistical analysis. I am Miss Mary Jane E. Torres, and we will dive in deeper in this lesson for today. Our objectives for today is at the end of the lessons or the seminar workshop, we are expected to identify the appropriate statistical tools for analyzing quantitative data and use the Jamovi software effectively in processing and analyzing the data. So, what is statistics? Statistics is the science of collecting, organizing, analyzing, and interpreting data in order to make sound decisions. It helps us understand information in a clear and systematic way, especially when dealing with numbers in real-life situations. Through statistics, we are able to gather data, arrange it meaningfully, and analyze patterns or trends that are not immediately obvious. So overall, statistics is a powerful tool that guides decision making. It enables us to understand the world better by turning raw data into useful information that supports reasoning, planning, and problem solving. So let's proceed to data. So what is the meaning of data? Data consists of information coming from observations, counts, measurements, or responses. So basically, it is information coming from responses of other people. So there are types of this. So what are the types of data sets? First is the population. The population is the collection of all outcomes, responses, measurements, or counts that are of interest. Next is the parameter, which is the numerical description of a population characteristics. Then the sample, which is the subset or part of a population. Then statistics, a numerical description of a sample or characteristic. So we have next is the branches of statistics. So there are two branches, which is the descriptive statistics and the inferential statistics. So first, let's define what is descriptive statistics. So descriptive statistics is the branch of statistics that involves the organization, summarization, and display of data. Next is inferential statistics. So inferential statistics is the branch of statistics that involves using a sample to draw conclusions about a population. So basically, inferential statistics goes step further. It allows us to use data from a sample to draw conclusions or make predictions about a larger population. Through inferential statistics, we can analyze or test hypotheses and make decisions even when it's not possible to collect data from everyone. While descriptive statistics focuses on organizing, summarizing, and presenting data, it shows by using tables, graphs, and average and other measures to describe information clearly. Overall, we understand that both these branches are important in statistics. So descriptive statistics helps us the data make sense, and while inferential statistics helps make conclusions and decisions beyond the data, making statistics a powerful tool in understanding real-world situations. Next is the types of data, the qualitative data and the quantitative data. The qualitative data consists of attributes, labels, or non-numerical entries, while quantitative data consists of numerical measurements or counts. So next, let's proceed to levels of measurement. So there are 4 levels of measurement. First is nominal. So nominal is a qualitative data which are categorized using names, labels, or qualities, and no mathematical computations can be made at this level. So basically, it is naming or labeling a data. Next is the ordinal. which is used in qualitative or quantitative data, which can be arranged in order, ranked, but differences between data entries are not meaningful. So ordinal level shows relative position but not exact differences. So in this level, data can be ranked, and intervals between values are not equal or known. For example, the class rank, the first, the second, and the third, or the satisfaction level, which is satisfied, neutral, or dissatisfied. Next is the interval level. So it can be ordered data, and meaningful differences between data entries can be calculated, and where zero entries simply represent positions on a scale, and the entry is not an inherent to zero. So zero does not mean none, but just a placeholder, label, or value, not a real absence. So in interval level, equal intervals between values. It shows meaningful differences. So what is the characteristic of this? Is that order data with equal intervals and no true zero, or zero does not mean absence. Next is the ratio. So the ratio is similar to data at the interval level, with the added property that a zero entry is an inherent zero, wherein a ratio of two data values can be formed so that one data value can be meaningfully expressed as a multiple of another. So for example, in this slide, so we will going to identify the level of measurement. So first is the nominal. So we can see here that the title of the data is Network Affiliates in Pittsburgh, PA. So WTAE, ABC, so it's, as you can see, it is continuous. WPXI is NBC, and so on. That is nominal. The next is the ratio. So 2009 American League home run total by team. So the ratio. Then the interval. So in New York's Yankees World Series victories years. Then the last one is ordinal. So the type 5 TV programs, as you can see here, that it includes the ranking of the top 5 TV programs, and that is ordinal. Next, let's talk about the Cronbach's alpha. So what is Cronbach's alpha? So it is used to measure the internal consistency, reliability of a set of items in a test, questionnaire, or scale, indicating how well the items consistently measure the same underlying construct. So Cronbach's alpha is a way of assessing reliability by comparing the amount of shared variance or covariance and among the items making up an instrument to the amount of overall variance. So the assumptions of Cronbach's alpha is items measure a single underlying construct, or the unidimensionality. Next is items are positively correlated with each other, which they have relationship with each other. Then data are continuous, or strict assumption are treated as continuous or common or like scales. So it is continuous in numbers. So next is no major measurement errors or badly worded items that violate item consistency. Next is the frequency distributions. So the frequency distributions, first is the frequency distribution table. So in this frequency distribution table, it shows classes or intervals of data entries with a count of the number of entries in each class. Next is the frequency count of a class. So the number of data entries in the class. So that is the frequency count of class. Next is the relative frequency of a class. The portion of or percentage of the data that falls into that class. So the formula for relative frequency is this. So as written in the slides, relative frequency is equal to class frequency over sample size. So the class frequency is symbol is F, small letter f, then sample size is small letter n. So sample relative frequency is equal to f over n, or divided by n. So the sum of the frequencies of that class and all previous classes, that is the relative frequency of a class. So note that the cumulative frequency of the last class is equal to the sample size n. Next is the graphs of frequency distributions. So these are visual tools used to present data from tables in a clear and understandable way. So they help us show patterns, comparisons, and proportions in the data. First is the histogram and the bar graph. So a histogram is used for continuous data and shows the frequency of values within class intervals. So the bars in a histogram touch each other to indicate that the data are connected and measured along a continuous scale, such as height, weight, or scores in a class. So in contrast, a bar graph is used for categorical or discrete data. Its bars are separated by spaces to show that the categories are distinct. Bar graphs are commonly used to compare quantities across different groups or categories. So the second one is the pie graph and donut graph. So a pie graph displays data as parts of a whole. Each slice represents a category's proportion or percentage of the total frequency. So this graph is useful when the goal is to show how the data are divided among categories. So for example, a donut graph is similar to a pie graph but has a hollow center. So it's like a donut, no? There's a hole in the center. So it serves the same purpose but can make the data visually clearer or allow spaces for labels or totals in the center. Third is the cube or the cube plot, neck, and other three-dimensional graphs. So there are many. These graphs are present frequency distributions in a three-dimensional form. Cube and cube plots and many more often used to show relationships also among multiple variables, adding depth to the data presentation. So by these graphs, we can visually imagine, or we can understand more the data that is presented. So as we can see here, these are the sample graphical presentations from Jamovi, Google Sheet, and SPSS. So for me, the most appealing or attractive to look at presentations is the Google Sheet. So it is highly recommended for students and teachers to use in a data presentation. So next is the descriptive measures. So first is the measures of central tendency. These are numerical descriptions that identify the center, middle, or typical value of a distribution. These are the arithmetic mean, weighted mean, median, and mode. Next is the measures of variation. So it describes the amount of dispersion or spread in a data set, indicating how much the data values differ from the mean or form each other. These are the range, variance, and standard deviation. So the descriptive measures is first is the measures of position. So it describes the relative standing of a data value by showing its rank, percentage, location, or distance from the mean in standard deviation units. So these are the factors such as quartiles, deciles, and percentiles. So it allows us to interpret individual values by identifying the rank. So percentage position and standard score location. Next is the box and whisker plot. So the box and whisker plot. So the box plot is based on the 5-number summary, which includes the minimum value, the first quartile, median, the third quartile, and the maximum value. So the box represents the middle 50% of the data, extending from quartile 1 to quartile 3. Inside the box, a line marks in the median, showing the central value of a data set. As we can see here in the slide, so it teaches us how to draw a box and whisker plot. First is to find the 5-number summary of the data set, which I tackled earlier. So second is to construct a horizontal scale that spans the range of the data. Next, plot the 5 numbers above the horizontal scale. Then draw a box above the horizontal scale from quartile 1 to quartile 3 and draw a vertical line in the box at quartile 2. Then the last one is draw whiskers from the box to the minimum and maximum entries. Next is the shape of distribution. So the shape of distribution describes how the data values are spread and arranged when shown in a graph, such as a histogram or box plot. Understanding the shape helps in interpreting the behavior and characteristic of the data. First is symmetric distribution. So a symmetric distribution occurs when the left and right sides of the graph are mirror images of each other. So the data are evenly distributed around the center, and the mean, median, and mode are approximately equal. So a common example of this shape is the normal bell-shaped distribution. Symmetric distributions indicate balance and data with no extreme skewness. So next, or the second one, is the uniform or rectangular distribution. In a uniform or rectangular distribution, all values or class intervals have roughly the same frequency, so they are different. The graph appears flat or rectangular, showing that no single value or range dominates the data. So this type of distribution suggests that each outcome has an equal or nearly equal chance of occurring. So the third one is skewed to the left or negatively skewed distribution. So a negatively skewed or skewed left distribution has a longer tail extending to the left side of the graph. Most of the data values are concentrated on the higher end. So while a few low values pull the distribution to the left, in this case, the mean is usually less than the median. So this shape often appears in the data where high values are common and low values are rare. Lastly, the skewed right or positively skewed distribution. So a positively skewed or skewed right distribution has a longer tail extending to the right. Most data values are clustered at the lower end, with a few high values stretching the distribution to the right. So here the mean is usually greater than the median, and this type of distribution is common in income, waiting time, or test score data where extreme high values occur less frequently. So in summary, the shape of distribution is symmetric, uniform, negatively skewed, or positively skewed. It provides important insight into how data are centered, spread, and influenced by extreme values. Next is the discrete and continuous probability distributions. So first is the random variable x. So it represents a numerical value associated with each outcome of a probability experiment. Then discrete. So discrete has a finite or countable number of possible outcomes that can be listed. The next is the discrete probability distributions, wherein a listing of all possible values of a desired random variable along with their corresponding probabilities. Then continuous, which has an uncountable number of possible outcomes represented by an interval on the number line. Then the continuous probability distributing is that a listing of all possible values of a continuous random variable. Next is national distribution, rather than normal distribution. So it is a continuous probability distribution for a random variable when its graph is called normal curve. Next, let's talk about the normal distribution. So a normal distribution is for the data with a symmetric or bell-shaped distribution. The standard deviation has the following characteristic. First is it's about 68% of the data within one standard deviation of the mean. Then second is about 95% of the data lie within two standard deviations of the mean. Then the last one is the 99.7% of the data lies within three standard deviations of the mean. Next is the sampling distributions and central limit theorem. So the sampling distribution is the probability distribution of a sample statistic that is formed when samples of size n are repeated taken from a population. The central limit theorem also forms the foundation for the inferential branch of statistics. Now, what is the central limit theorem? So it states that for a sufficiently largely sample size, the sampling distribution of the sample means will be approximately normal, regardless of the shape of the population. So it tells us that when we take repeated random samples, the distribution of the means becomes more normal and the sample increases. So the mean of the sample means equals the population mean. The spread of the sample means because as smaller a sample size increases you, and we can use normal probability methods to make inference about childhood. So we can use normal probability methods to make inferences about population mean. Next, so we're talking about the normality test. So these are statistical tests used to check whether a set of data comes from a normally distributed population, which is an important assumption for many parametric tests. So the common normality test includes the Shapiro-Wilk test, which it is very common and powerful for small moderate samples. Next is the Kolmogorov-Smirnov test with daily force corrections compares the sample distribution to a normal distribution. Next is the Anderson-Darling test. It gives you more weight to the toes of the tails of the distribution. Next is the confidence intervals. So confidence intervals are a key concept in inferential statistics. So they provide a range of values that is likely to contain the true population parameter. So it is an estimated range of values calculated from a sample. It is used to estimate an unknown population parameter together with a confidence level. So what is its purpose is that it estimates population parameters. It measures the precision of a sample estimates. So the confidence intervals has three main parts, which is the point estimate, margin of error, and confidence level. So the point estimate points that a single value from the sample. So it is a single value from a sample. Margin of error, or ME, is the amount added and subtracted from the point estimate. Third is the confidence level, which is the degree of certainty, or commonly 90%, 85%, or 99%. So the formula, or the general form of confidence interval is equal to point estimate plus or minus net margin of error. Next topic is all about hypothesis testing. So hypothesis test is a process that uses sample statistics to test a claim about the value of population parameter to make informed decisions. Then, statistical hypothesis is a claim about a population. It is a claim about the population parameter that can be tested using sample data through the procedures of hypothesis testing. So the purpose of hypothesis testing is to use sample data to decide whether there is enough evidence to reject or fail or to reject the claim. So next is the null and alternative hypothesis. The null hypothesis is a statement of equality involving the population parameter, a hypothesis that is assumed true unless there is sufficient evidence to the contrary, while the alternative hypothesis is a statement that must be true if the null hypothesis is false. It reflects the claim that the researcher or study aims to support. So, the role of the statistical and hypothesis in hypothesis testing is that the hypothesis testing uses sample statistics to evaluate the truth of claims and about population parameters. So, the evidence is judged based on the significance level alpha. So, the conclusion is either reject the hypothesis or fail to reject the hypothesis. We never accept hypothesis, we only fail to reject it if the evidence is insufficient. So there are two types of errors, the type 1 and the type 2 errors. So these errors in hypothesis testing are the mistakes that can be made when using sample data to make decisions about the population. So type 1 error occurs if the null hypothesis is rejected when it is true. Type 2 error occurs if the null hypothesis is not rejected when it is false. Type 1 error is false positive or rejecting a true hypothesis. It is false alarms are harmful and lead to wrong decisions and unnecessary actions, especially about safety concerns, while the type 2 error is false negative. Failing to reject a false hypothesis is missing a problem, leads to danger or lost opportunities. Next is the level of significance. So, you will reject the null hypothesis when the sample statistics from the sampling distribution is unusual. You have already identified unusual events to be those that occur with a probability of 0.05 or 0.05 or less. When statistical tests are used, an unusual event is sometimes required to have a probability of 0.10 or less, 0.05 or less, or 0.01 or less. Because there is variation from sample to sample, there is always a possibility that you will reject a null hypothesis when it is actually true. In other words, although the null hypothesis is true, your sample statistic is determined to be an unusual event in the sampling distribution. You can decrease the probability of this happening by lowering the level of significance. So, level of significance is defined as the maximum allowable probability of making a type 1 error. It is denoted by A in the lowercase Greek letter alpha. The probability of type 2 error is denoted by B, the lowercase Greek letter beta. Next is the p-value or the probability value of a hypothesis test. A probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. So the decisions rule based on the p-value is to use a p-value to make a conclusion in a hypothesis test. Compare the p-value with A. So if P is less than or equal to A, then reject the hypothesis. If P is greater than A, then fail to reject the hypothesis. Next one is the parametric test for difference analysis. So first is the one sample t-test. So it is used to determine whether a sample mean significantly differs from a known or hypothesis population mean when the population standard deviation is unknown. So the assumptions of the one sample t-test is the sample is randomly selected from the population. The variable is measured on an interval or ratio scale, or the data come from a normally distributed population, or the sample size is sufficiently large for robustness. Observations are independent of each other. For the non-parametric test for difference analysis, the one sample Wilcoxon signed rank. So it is used to determine whether the median of a single sample differs significantly from a hypothesized population median when the data are not normally distributed. So the assumptions of one sample Wilcoxon signed rank is that data are paired with a hypothesized median. So one sample or matched to a constant. So the variable is at least ordinal or rankable. The differences between observations and the hypothesis median are symmetrically distributed, and observations are independent of one another. Next, for the parametric test for a difference analysis. First is the independent sample t-test, used to determine whether the means of two independent groups significantly differ from each other. So the assumption is that the two groups are independent or no participant is in both groups. Next is the dependent variable is measured at the interval or ratio level. Then each group's data came from a normally distributed population. Then the variance of the two groups are equal, or homogeneity of variance. Next is that observation within each group are independent. Next is the parametric test for difference analysis, the Wilks t-test. So it is used to compare the means of two independent groups when their variance are not equal, or heterogeneous variances. The assumptions of this is: first, the two groups are independent; two, the dependent variable is measured at the interval or ratio level. Next, each group's data are approximately normally distributed. Then lastly, the observations are independent within and between groups. The Wilcoxon rank sum test, or Mann-Whitney U. So this is another difference analysis in non-parametric test. So it is used to compare whether two independent groups differ in their distributions, typically their medians, when the dependent variable is ordinal or not normally distributed. So the assumption is that the two groups are independent. The dependent variable is at least ordinal or rankable, so it can be rankable. Then the distributions of the two groups have the same shape for median comparison, so observations are independent within and between groups. For parametric paired sample t-test, so it is used to determine whether the mean differences between the two related or matched or repeated measures observations is statistically significant. So the assumptions of it is the two sets of scores are dependent or same participant or matched pairs. So they have same participants. Then the dependent variable is measured at the interval or ratio level. The differences between paired scores are normally distributed, and while the pairs are not randomly selected, and observations within pairs are independent from other pairs. So in non-parametric test for difference analysis, Wilcoxon-signed rank test. So it is used to determine the median differences between two related, paired, or repeated measures. Observation is significantly different from zero when the data are not normally distributed. So the assumptions of it is the two sets of observations are paired for dependent. So some participants are matched pairs. Then the dependent variable is at least ordinal. The difference between paired observations are symmetrically distributed, and the last is pairs are randomly selected and are independent from other pairs. Next, for the parametric test for difference analysis is one-way ANOVA analysis of variance. So it is used to determine whether these are significant differences among the means of three or more independent groups based on one categorical factor. So the assumptions of one-way analysis of variance is the groups are independent. Second, the dependent variable is measured at the interval or ratio level. Third, the data in each group are approximately normally distributed. Fourth, the variance of the groups are equal or homogeneity of variance. Fifth is the observations are independent within and between groups. So for the non-parametric test for difference analysis, the Kruskal-Wallis test. So it is used to determine whether three or more independent groups differ in their distributions. So typically their medians when the dependent variable is ordinal or not normally distributed. So the assumptions of it is, first, the groups are independent. Second, the dependent variable is at least ordinal or rankable. Third, the distribution shapes of the groups are similar for valid median comparison. Then fifth is the observations are independent within and between the groups. Post analysis, use this when you found a significant ANOVA result and want to know which groups differ. So we can use this now. So first is the two-case HSD, most common controls type 1 error. The games how well best when variance are unequal or homogeneity of variances is violated. Since Kruskal-Wallis in non-parametric uses pairwise comparisons with adjusted p-values, Steele, Critchlow, Flener. Chi-squared goodness of fit test. It is used to determine whether the observed frequencies in one categorical variable significantly differ from the expected frequencies based on a hypothesis distribution. So the assumptions of chi-squared is, first, data are frequencies, 9 counts, not percentage or means. Second, categories are mutually exclusive. Each case fits in only one category. Third, observations are independent of each other. Fourth, expected frequency in each category is at least 5 or most categories greater than or equal to 5 with no very small expected counts. Next is the parametric relationship analysis. So the other type of parametric relationship analysis is the Pearson product moment correlation coefficient. It is used to measure the strength and direction of the linear relationship between two continuous variables. So the assumptions of the Pearson product is both variables are continuous. It is interval or ratio. Second, the relationship within the variables is linear. Third, the variables are approximately normally distributed. Fourth, there are no significant outliers. And fifth, observations are independent. So for the non-parametric, another one is the Spearman rank correlation coefficient rho, used to measure the strength and direction of a monotonic relationship within two variables when data are ordinal or not normally distributed, or when the relationship is not strictly linear. So the assumptions of it is that observations are independent, variables are at least ordinal or can be ranked, Then third is the relationship is monotonic. As one variable increases, the other tends to consistently increase or decrease. Fourth is that no excessive ties in the ranks or ties are handled with appropriate correlations. So for the non-parametric relationship, another one is the Kendall's tau b. It is used to measure the strength and direction of association between two ordinal variables adjusting for ties in the data, and is especially useful for small samples or many tied ranks. So the assumption is that both variables are at least ordinal or can be ranked. Observations are paired and independent. Each pair of scores comes from one subject or case. Then third is that the relationship is monotonic. As one variable increases, the other tends to increase or decrease and consistently. Next is the point biserial correlation. So it is one of the non-parametric tests for relationship analysis. So it is used to measure the strength and direction of the relationship between one continuous variable and one truly dichotomous variable. For example, the pass or fail, male, female, yes or no. So the assumptions of it is that one variable is continuous interval or ratio. Another one is that the other variable is genuinely dichotomous or two real categories, not artificially split. Third is that the continuous variable is approximately normally distributed within each group of the dichotomous variable. Fourth is the relationship between the continuous variable and the dichotomous groups is linear. So observations are independent. Then let's go to the regression analysis. So the regression analysis is a family of statistical techniques used to model, predict, and explain the relationship between a dependent variable and one or more independent variables. So the simple regression analysis is used to predict the value of one continuous variable. So the continuous variable here is the dependent variable. Based on continuous predictor, which is the independent variable, and to determine whether a linear relationship exists between them. So the assumption of simple regression analysis is the following. First is the relationship between x and y is linear. Second is the observations are independent. Third, residuals are normally distributed. Fourth, homoscedasticity or residuals have constant variance across levels of x. Next is that independent variable is measured without error. Another is the multiple regression analysis. It is used to examine and predict the value of one continuous dependent variable from two or more independent variables or predictors, and to see how strongly each predictor is related to the outcome while controlling for the other. So the assumptions of this multiple regression analysis: first is the linear relationship between each predictor and the dependent variable. Second, independent observations. Third, residuals are approximately normal. Fourth, homoscedasticity or residuals have constrained variance across predicted values. Third is no multicollinearity or predictors are not excessively correlated with each other. Then last is that predictors are measured without serious error. So that's end our lesson for today. Thank you so much. Again, this is Miss Mary Jane Itores.